Hey Science 2 kiddos, just going to use these slides as a quick review of the pressure unit conversion and Boyle's law, which we covered in our previous class. So here's an example problem. What pressure in kilopascals and in atmospheres, so this is kind of a two-part question, does a gas exert at 385 millimeters of mercury? So that's our starting unit. So we need to convert that into kilopascals and into atmospheres. And so I'll do the kilopascal calculation as an example, and I'll leave the atmospheres to you to do. So as always, start off with the unit you've got, which is 385 millimeters of mercury. We're going to multiply that by a fraction. This is our conversion ratio. You always put the same unit that you want to convert on the bottom, because we want those to cancel each other out. And we want the unit on top that we want. Again, I said I was going to do kilopascals as an example, so I'm going to put kPa on the top. And I know then my answer is going to be in kilopascals. So again, the trick is to find that relationship, right? What's the relationship between millimeters of mercury and kilopascals? And there it is right there. I know that 760 millimeters of mercury is equal to 101.3 kilopascals. There you go. And so you're just going to do 385 times 101.3 divided by 760. So you multiply those two, and then the product of that, divide that by 760, and you'll get something like 51.3 kilopascals. Okay, I would like you to do the same conversion from 385 millimeters of mercury to atmospheres. So give that a go. Once you're done, you can cross-reference your answer here. Should have gotten something like 0.507. And again, here's the example setup. Notice kilopascals was put on the bottom, atmospheres on top. And again, you know that one atmosphere is equal to 101.3 kilopascals. So that's where those came from. All right, and we discussed Boyle's law. This is the first of the gas laws that we covered. It's looking at the relationship between pressure and volume, and again, it states that pressure is inversely proportional to volume. In other words, when one goes up, the other goes down. You write the equation like this. You don't have to memorize this. This will always be provided to you. And again, the units can vary. It's just as long as they're matching, right? As long as the unit for P1 is the same as the unit for P2. So if P1's in atmospheres, P2 has to be in atmospheres. Volume's the same way. If this volume's in liters, then the second volume also needs to be in liters. As long as they match, the math should work out. Now notice, we're ignoring temperature, and we're ignoring the amount of gas, the moles. So don't worry about moles, don't worry about temperature here. We're assuming they are kept constant. So again, I'll just walk through an example problem and then have you work on one. If I have 5.6 liters of a gas in a piston at a pressure of 1.5 atmospheres, so right there, that's my V1 and my P1. And compress the gas until its volume is 4.8 liters, there's my V2. What is the new pressure? So I need to find P2. And automatically I can see that I am reducing the volume, right? From 5.6 to 4.8. So I know that my pressure is going to go up. I know my P2 should be higher than 1.5. But again, let's just set it up into the actual equation. So again, if I'm using this, P1V1 equals P2V2, then I'm going to go ahead and do 1.5 atmospheres times 5.6 liters is equal to our unknown P2 times 4.8 liters, which is the new volume. And again, just going to divide both sides by 4.8 liters. So those will cancel out, and we're just left with P2. And now we got 4.8 liters over here. So I just solve for that. 1.5 times 5.6 divided by 4.8. And I find that my P2, and again, you'll notice that liters will cancel out. You're left with the unit atmospheres. My P2 will come out to be 51.3 kp. Oops, my bad. I'm looking at the wrong thing here for my answer key. Sorry, the P2 that you should get is 1.8 atmospheres. And notice that that is higher than 1.5, so that makes sense, right? The pressure did go up. So go ahead and try this problem number 2 on your own. Once you're done, you can cross-reference the answer with the answer key here. In this problem, you are given the initial volume and initial pressure. You are then given a second pressure. You've got to find the second volume, the new volume. What they call X is V2. And you should have gotten something like 18 liters. In reality, there's a couple of examples. We mentioned Bob Gardner's balloon. So you might have noticed this isn't exactly what this diagram is showing, but just as a kind of demonstration. Imagine Bob Gardner's balloon when he started off on the ground looked like that. And then by the time he reached 49,000 feet, it had expanded to look like this. And again, that's because when he was on ground level, there's an immense amount of atmospheric pressure that was condensing that gas volume down, right? High pressure, low volume of gas. But as he rose higher and higher up in the atmospheric pressure was much less, and therefore the volume of the balloon he was in expanded. So kind of a nice example of that inversely proportional relationship. Same thing with scuba divers, right? What they experience when a scuba diver goes deeper and deeper in the water, their ears begin to hurt a lot, and that's because normally at sea level, the airspace that is within our ear, your inner ear, the air in there, is at an equal pressure to the outside air. However, when you're scuba diving underwater, there's a huge amount of pressure now pushing in your ear from the water, and that's going to be crushing the organs in here, right? Because the gas inside your ear is getting smaller, and so you have to equalize. You have to kind of forcefully blow into your nose while blocking your nose. That brings more air back in to do that. So just 2 nice real-world applications. Hope this was helpful. Thanks.